Okay, Kepler came up with some ideas in regards to planetary motion that we've gone through already. Each planet travels an elliptical orbit around the sun. The sun is one of the focal points. Imaginary line drawn from the sun to a planet sweeps out in equal areas and equal time intervals. And the third one is the square of the planet's orbital period. T squared is proportional to the cube of the average distance between the planets and the sun. T squared is going to be proportional to r cubed. And looking at Newton's idea, Newton used Kepler's idea law to support the law of gravitation. What keeps orbits nearly circular, centripetal force, is the force of gravity. Once again, that force of gravity between planets and the Earth and the Sun and the orb or the satellites, the moons that go around the planets, all these things work in conjunction in regards to keeping Earth where it is in its orbital path. Once again, if you would start eliminating planets out of the solar system, that would affect Earth's orbit around the sun. And when you start affecting Earth's orbit around the sun, we're either going to get closer, we're going to get further away. It's either going to get a little bit warmer or it's going to get a little bit chillier. Okay, global warming. They worry about global warming. You take a few planets out of the solar system, and you'll have some issues climate-wise. Okay, T is a period of revolution around the orbital period. 2 pi r is your circumference, your distance of revolution, whatever the distance of revolution. And once again, we are not perfectly circular, but we are close. We are close to being circular, so we could do an average of the radius going around the planet or around the sun. Orbit is the radius, r is the radius of orbit. Mass 1 and mass 2 are mass 2 is the mass of the object being orbited. Mass O is mass of the object. We know we can calculate your velocity, your average tangential velocity. This is an average here. This is an average. By calculating the circumference, the distance that's being traveled by a planet or a satellite, and we divide that by the amount of time it takes for one time around. Okay, that is the orbital period, a period of revolution. Okay, this is a period of revolution. 2 pi is the distance that you're traveling, that a planet is traveling. This gravitational force between the objects is equal to the centripetal force. What keeps objects going in a circular path? It is the gravitational pull between objects. Without gravitational pull, once again, we don't maintain circular paths. So what we talked about on Friday is this gravitational pull is calculated by G, which is a value that was established by Cavendish, times the mass of the object, mass of the two objects, the product of the two masses, divided by the length or the distance between the two objects. This r was the distance between the two objects, and this is what we talked about on Friday. We also talked about last week centripetal force. Centripetal force Centripetal force is mass times centripetal acceleration. And how we calculated centripetal acceleration was v squared divided by r. So we have these two things that are going to be equal. They have to be equal. They have to be, if we have to have equality there, for us to have circular paths or close to circular paths, okay, we have to have a centripetal force between the bodies, but we also have to have a gravitational force between these two bodies. They have to be the same. Well, if we take a look at these equations here, or these two values, quantities, the masses of these objects will cancel out. They will cancel out. We have a radius squared here. We have one of the radii here. One of these will cancel out. So we have some cancellation. Substituting in for my tangential velocity. What we are left with here, let's clean this up a little bit. We have a G still left over here. We still have an M2 left over here. We still have a radius left over here. On the right-hand side, we have 2 pi r divided by p, or t, and that is squared. All we're doing is we're making a substitution. Tangential velocity we can calculate by the average, or the circumference divided by t. Using some algebraic skills, we have g m2 over r is equal to 4 pi squared r squared over t squared. All we're doing is we're distributing my exponent of 2 to every one of my terms. Multiplying both sides, I'm going to clear my fractions out here to clean this up a little bit. So I'm going to multiply by the t squareds over here. That will cancel out my t squareds. I'm going to multiply by the r to cancel out these two r's. So what we're left with is we're left with t squared g m2 is equal to 4 pi squared r cubed. what I did is I pulled the r cubed out. The reason why I pulled the r cubed out, we have a 4, we have a pi squared, we have a g, and we have an m2. These are all constants. These are all constants. The 4, the pi, the g, and the mass, they're constant. They're not going to change. What this supports then is supports Kepler's third law. Kepler's third law. The square of the planet's orbital period, t squared, is proportional to the cube of the average distance, r cubed, between the planets and the sun. What we have here is we have t squared is equal to some constant times r cubed. This is a constant, which is an idea of proportionality. They are directly proportional. If we take the square root of both sides here, what we're left with is t is equal to 2 pi square root of r cubed gm2. Once again, these are things I would get down. Orbital speed can be calculated by gm2 divided by my radius. Once again, those are two things I would add to your equation sheet. Weight is the downward force of mass. Weight is the downward force of a mass. If you step on a scale, it is measuring, you step on it, it says 150 pounds. Okay, what is that measuring? That's measuring your downward force. If I put this on the spring scale, this is measuring a downward force. So you're measuring a downward force. But what we want to talk about once again, though, is if you step on a scale, okay, it measures how much force you're pushing downwards on it. That's what the little dial or the little digit reads up then. How much downward force do you have? So when you have this downward force, you have Newton's third law. Every force, there's an equal but opposite force that's pushing upwards. Newton's third law. Newton's third law, for every force is an equal but opposite force. There's a normal force pushing upwards, because when you step on the scale, you don't fall down through the floor. You don't break the scale. The scale doesn't go away. The scale continues to push back up at you. For every force, there's an equal but opposite force. Well, suppose you put a scale on an elevator. You put a scale on the elevator, and you step on that scale. It's going to measure your weight. Your normal weight is measured. What would happen if you stepped on the scale and the elevator goes on a free fall? What do you think would happen to your weight on the scale? You're standing there, you step on the scale, and all of a sudden the elevator starts to free fall it. It'll put its brakes on before you hit the floor, hit the ground. But it starts to free fall. What happens to your weight? Is it going to be the same? No. The reason why is the floor is not pushing back up at you. The floor is going down. What you basically start to experience is the idea of weightlessness. No normal force, measured weight is decreased. You maybe have some weightlessness, because the scale is not going to measure any of your weight, because the scale is falling away from you. There is no upward force pushing back upwards. Or if you step on the scale in your bathroom, you have the floor underneath the scale that's pushing back up on you. This is sometimes what you feel on roller coasters. The idea of weightlessness. Because basically, if you went on the demon drop, up at Cedar Point, anybody ever do that? Nobody ever did the demon drop? The Power Tower, is that the one that goes way up, curves, and then comes back down? The demon drop, basically, it takes you all the way up and then lets you go, and you fall straight. And then, yeah, same idea. Same idea. Well, in that, basically, your seat is being removed from underneath you, and you are experiencing the idea of weightlessness. Because there's no weight, there's nothing holding you. What if the elevator was moving upwards? What happens? Your normal force is increased. And your measured weight is increased also. Because the floor is pushing additional weight against you, or a force against you. Astronauts experience weightlessness. your gravitational force is equal to your centripetal force. John Glenn, in 1962, John Glenn was the first astronaut to orbit the Earth in a spaceship called the Friendship 7. His maximum height was 262. His minimum height was 660 kilometers. Use the average of these two to calculate the orbital period and the tangential velocity of Friendship 7. The mass of the Earth is 5.97 times 10 to the 24th kilograms, and the radius of the Earth is 6.38 meters times 10 to the 6 meters. So we have this Earth, and then we have the spaceship up here that is orbiting the Earth. The maximum or the minimum height was 160 kilometers, and the height maximum was 272 kilometers. So your minimum was 160, and the maximum was 262 kilometers. We have the mass of the Earth is 5.97 times 10 to the 24th kilograms. We have the radius of the Earth, which is 6.38 times 10 to the 6 meters. Calculate the orbital period and the tangential velocity. The orbital period is equal to your 2 pi square root of r cubed divided by gm. All right, we need to find the average of these two. So it'd be, let's see, 262 plus 160, 422, 211. So your average radius is 211 kilometers. So the average is 211 kilometers above the Earth's surface. But what is your radius of the circular path? what do we have to do to find the radius of the circular path? Because we need to have the radius here of the circular path. How do we find that? Yeah, add them together. But one's in kilometers and one's in meters. So we need to convert them all to the same. Well, what's our G value? Is our G value in meters or kilometers? 6.67 times 10 to the in meters. So we want to convert these into meters. So we have 6.38 times 10 to the 6 meters. So we can move the decimal point 1, 2, 3. Let's see, 1, 2, 3, 4, 5, 6. So we have 6,380,000 meters. 1, 2, 3, 5, 6. And our 211 kilometers we'd have to move it 3 decimal places, so we're going to have 3 zeros there. You have 211,000 meters. So our radius of rotation for the spaceship is 6,591,000 meters. So we have 2 pi square root of a bunch of really big numbers. 6591000 cubed over G, which is 6.67 times 10 to the 28th. Is it 6.67 times 10 to the 28th or 24th? I can't remember what G is. Oh, it's negative. That was wrong direction. The negative 11th, yeah, it's really small. And this is times the mass of the Earth, which is 5.97 times 10 to the 24th. So once again, this becomes a calculator exercise. You need to make sure you quantify these on the bottom. So you have 6591000 divided by quantity 6.67 e to the negative 11 times 5.97 e to the 24th. I forgot to cube that. 5327.9, maybe. Yes. Once again, you really have to watch your calculator, what you're doing with your calculator. All right, because you have the 6591 000 cubed divided by, you have to quantify your 6.67 e to negative 11 times 5.97 e to the 24th and we have to square root that. So you have 847.96 that you have to multiply by 2 pi. Did I? 6591. 1, 2, 3, 4, 5, 6. Which would be 1, 2, 3, 4, 5. But when I added the 211,000, it eliminated one of my zeros. So when I added there, I got 0, 0, 0, those 3 zeros, but then I have a 1, a 9, a 5, and a 6. Okay, then our tangential velocity, our average velocity, can be calculated by my GM2 divided by my radius. Just my radius. And then we'd have to square root of that. 7772.7. Maybe. All right, tomorrow we will go through the last problem here, dealing with going around a circular path, gearing towards a quiz on Wednesday or Thursday, one of the two. Like get a quiz in for the end of the 9 weeks. Here's the homework for this chapter. And once again, steered towards a quiz. I'd like you to run it on Wednesday, but if we need to stretch it to Thursday, that's fine. And have a good day.